This is the 36th lecture and we are going to complete that classification of random processes, and also if time permits we would like to introduce the correlation functions. But before doing anything else, I must clarify some of the confusions with which I left you in the last lecture. Was it yesterday? Thursday, yeah. This was about the discrete probabilities. There are two things that one has to consider. One is, if the events are not graded, for example, take the example of that box containing multicolored balls, green, black and white. Now, green, black and white have no gradation, and therefore you consider the probability. I want your attention because I am clearing a confusion. We consider the probability of picking up, let us say, a green ball. All right. This is the probability. This is a point probability. Green is green. No relation with black. There is no gradation. Green is not greater than black, or black is not greater than green. On the other hand, a discrete random process is defined as one. I am going back to classification. I said there is a continuous random process in which the random variable, in a continuous random process, the random variable capital X can take a continuum of values. That is, it can take values anywhere at any value between any value within a range. The range could be as large as minus infinity to plus infinity. On the other hand, a discrete random process is one in which the random variable can take only discrete values. It does not mean that the variable small x, well, this is continuous. On the other hand, the probability, well, no, let me take an example. Suppose I take a time function which, let us say, varies like this. There are two different things that one must not confuse about. The time function, it is not a discrete function of time. Time is not discretized. Time is still continuous. It is the values of x that are discretized. In this example, for example, the values of x are 0 and let us say x0. That is, the random variable capital X can take only one of the two possible values, perhaps with equal probability, perhaps not. All right. So, this will be called a discrete random process. A discrete random process is one. Forget about that green, black and red. That is completely discrete probability. Discrete probability and discrete random process are quite different. A discrete random process is one in which the random variable capital X can take only specified discrete levels. For example, in this particular case, it is either 0 or x0. We could also complicate the process by saying, let us say, it can also take a value of minus x0. Then the quantized levels, there are 3 in number, plus x0, 0 and minus x0. This is the definition of a discrete random process. Now, with regard to a particular example now, capital X is the random variable and small x is the value that it can take. All right. Small x of t is the random time function. Okay. Now, let us take this example. Is this okay, or shall I draw it separately? Can you see what is? Okay. I have taken a specific example to illustrate this concept of probability distribution function and probability density function in the case of a random process, in the case of a discrete random process. This is the function. This is the function x of t, where we assume that x of t, the random variable associated with this random time function, can take on only two discrete values two discrete levels. One is, let's say, 0, the other is 100, just for example. It could be a voltage sample. Now, which means that after reaching this point, well, after reaching this point, it could either remain at 0 or it could again go to 100, all right, with equal probability. That is, the random variable capital X could take one of the two values, 0 and 100, with equal probability. That means the probability that the random variable takes on a value 0 is half. The probability, I am not saying distribution or density, simply the probability, and these are point probabilities. That is, small x can take either a value of 0 or 100, point probability, no range, all right. So these are genuinely discrete probabilities, okay. So if I plot the probability that capital X takes a value 0, obviously it is half, all right, the probability is half, and the capital X takes a value 100 is half, and the sequence, the probability is now a sequence, the probability is a sequence which has only two values, that is half delta n plus half delta n minus 100, not n, okay, you can take it n is an integer, all right, delta n, half times delta n plus half times delta n minus 100. This is indeed a discrete probability. Now, when you say probability distribution function, the definition is, as done earlier, the definition is the probability distribution function capital P of x is defined as the probability that the random variable assumes a value less than equal to x. This was the definition. The probability and probability distribution function are quite different, and therefore even for a discrete random process the definition is meaningful. For example, in this particular case you can see that from minus infinity to 0 the probability distribution function P of x is also 0. At x equal to 0 suddenly it jumps to half, all right, it jumps to half, then it remains at half. For example, if you ask what is the probability distribution function for, let's say, x equal to 70, that is capital X less than equal to 70, it is still half, all right, it is the cumulative function, it is the integrated function, all right, so it is still half, it remains at half, then at a small x equal to 100 suddenly it jumps to 1, it was already half, another half is added, and therefore it jumps to 1, and it remains at 1, taking probability, let's say capital P of 200 will also be equal to 1, all right. So this is the probability distribution function, and one must clearly understand that point probabilities, which is this graph, and probability distribution function are quite different. Probability distribution function has a range associated with it, and the definition is that the random variable takes on a value less than or equal to the argument of capital P. And naturally then the probability density function also assumes a meaning. You see, if I differentiate this, then obviously I will get delta functions at 0 and at 100, all right, both of strength half, which is a reflection of the point probability, that is this graph. This is a reflection. This is a sequence, and this is a sequence of impulses. This is a sequence of samples, and this is a sequence of impulses, all right. Is the point now clear? The distinction between continuous random process and discrete random process. The thing to remember is two things. One is that in the discrete random process the time is not discretized. What is discretized is the value that the random variable can take. Therefore, it is the amplitude which is discretized. Number two is that the probability, point probability and probability distribution function are different. Point probability is associated with a single event occurrence at a single value of the random variable. On the other hand, the probability distribution function is associated with a range, and it is a cumulative range. Probability distribution function can never be negative. It lies between 0 and 1, all right. the maximum value is 1, and the differentiation of a staircase like function like this obviously is a sequence of delta functions. Alright. Then we go to the other classifications, that is alright. Did I introduce the terms deterministic and non-deterministic? Yes, I did. Yes.
So this means that we can't talk of px and small px for processes like those of balls.
No, they were because there is no gradation. There is no gradation. It can take 3 discrete colors, but there is no gradation. You can't say black is greater than red, or unless you can assign a code. For example, you can say green is 1, black is 2, and white is 3. Then there is a point in defining a probability distribution function. All right, not otherwise. That is correct. Just like small x, capital X could take values between only 0 and 100. Similarly, 1, 2, 3. This is an artificial coding that you introduce, or maybe according to wavelength. There are 3 wavelengths, and you can make a gradation. Then probability distribution function will make sense, not otherwise.
So in this case, we cannot have negative impulses.
We cannot have negative impulses because P of x is a non-decreasing function of x.
So what is the counterpart of time in this ball example?
What is the counterpart of time? There is no counterpart of time.
We can have negative impulses. Why not?
No.
So suppose in this case what you took was that for x equal to 0 it was half, and x equal to 100 it was also half. Suppose we don't have a situation like this. We have that x of 0 is half.
Yeah.
And
x of 100 is minus half.
No, not minus half. It is half.
Okay, you give up.
It could be say 1/4 and let's say at 200.
It doesn't matter. It still shall be.
Go on summing up.
Go on summing up because it's cumulative. It's a non-decreasing function. Alright, deterministic and non-deterministic we have already explained. Most of the random processes are non-deterministic. In fact, deterministic random process is a kind of an artificial term, as I have defined, and I have given you an example, a cosine omega t plus theta, where theta is the random variable over an ensemble, may be uniformly distributed over a range of 0 to 2 pi, then p theta, small p of theta would be 1 by 2 pi, between theta equal to 0 to 2 pi, but for one member of the family, theta is a constant, and therefore values of the random variable can be predicted. In that sense, it is deterministic, but it is random in the sense that theta is a random variable. We next consider another important basis of classification, that is stationary and what is the other thing called? Non-stationary. And you must understand this carefully. Although I am introducing a large number of terms, I am trying to go as slow as possible so that the concept sink in. A stationary process is one. Well, let's take an example. Let's say we have a random time function x of t, one sample from an ensemble like this. No, it cannot be multi-valued, sorry. Maybe it is like this, okay. And we consider 2 time instants. Let's say t1 and t2. Then we can define a random variable x1, which is x of t1, and x2, which is x of t2. All right. And I can consider the total ensemble and find out all possible values of x1 and x2. The probability is specified because I have said it's an ensemble. Now, the probability density function can be defined for x1 as well as for x2. The probability density function can be defined for x1 as well as for x2. A stationary process is one in which these are equal. That is, the probability density function for a single random variable, I insist, I emphasize this, there is a single random variable that we are considering. In case of joint, we shall have to make a modification of this definition. But for a single random variable, the probability density functions, and in fact all ensemble averages of the form standard deviation or variance or mean value or mean squared value, they are all independent of where you take the time origin or where you take the time. Alright, I have only shown one example, that is the density function. Alright, it is true for all ensemble averages. If the density functions are identical, then obviously the averages shall also be identical. Alright, this is the meaning of a stationary process. On the other hand, if the probability density functions depend on which time we observe the random variable, that is, if you have to write P of x1 and also the time origin to be able to specify the probability density function, then it is a non-stationary process. In other words, Px1 t1 is not equal to Px2 occurring at t2. This will be called a non-stationary process. Yes.
Sir, here the x1 is the counterpart of capital X.
Capital X is the name of the random variable. Alright, small x1, alright, small x1 is the random variable here. We are considering two random variables, small x1 and small x2. Small x1 is the value of x at time t equal to t1. Small x1 itself varies over the ensemble. Okay. Now consider two random processes.
Excuse me, sir?
Yes.
So for a process to be stationary, is it necessary that Px1 equal to Px2 for all x1, x2, or for particular choice of x1 and x2?
For all x1 and x2. That is for all t1 and t2.
That would mean
The time origin is not important.
so that would mean that xt is equal to is a constant.
No, xt is not a xt is a random time function.
So can we have a stationary process for that matter?
Yes, of course. Most of the processes can be approximated as stationary. For example, you take 1000 resistors, 1K resistors, and suppose we put 1000 boys to record over the same time interval the noise waveforms. Well, it's a stationary process. The probability distribution function, probability density function is the same. Where you measure the random variable. You take the records and then measure the random variable at different instants of time, find out the probability density function, it will be identical. On the other hand, yes,
T1 and T2, how did you choose T1 and T2?
it is independent of, they are independent of T1 and T2. That is, the time origin is not important. We could as well choose T3. But suppose now, from the same random process, we take two random variables, x1, x2, and find out the joint probability density function. Obviously, the joint probability density, not the individual probability density function. We find out the joint probability density function, that is the probability of occurrence of both x1 and x2. That is, capital X takes a value less than equal to x1, capital X takes a value less than equal to x2. The joint probability. Obviously, in general, there will be functions of t1 and t2. Alright? Now, suppose we take the same functions, same variables at two different instants of times. Let's say t1 prime and t2 prime, and call these x1 prime and x2 prime. Another probability density function. Alright? In general, they will depend on the times of occurrence. If it is joint, obviously, it is important where these times are. But if the probability density functions, if these two are equal, with t2 prime minus t1 prime equal to t2 minus t1, what does it mean? That means the probability density function depends only on the time interval, but not on the origin of time. That is where we chose the time reference or the time origin. If this is the case, then we say it is a stationary random process. It is a stationary random process.
So it's like question here, x1 and x2 are constants or they are variable? Over
They are variables.
They are variable.
Yeah.
Over ensemble.
Over the ensemble, not over time. What we have chosen is we have taken times t1 and t2. Then we shift. We go to some other values of t1 prime and t2 prime. And we find the probability density function. If these two are identical with the interval being the same, it means that where you chose your time origin is not important. You know, t1 prime and t2 prime, obviously you can make them equal to t1 and t2 by shifting the origin, right? And therefore the origin of time is not important. Similarly, it can be extended to many more multi-valued probability density functions. You could have 3 random variables, you could have 4 and so on. If suppose we have 3, then let's say x1, x2, x3, then it should depend on t3 minus t2 and t2 minus t1. Do I also require t3 minus t1? No, because that is fixed if this is fixed. Alright. So the probability density function, if it depends only on these intervals, but not on the absolute values of t1, t2, t3, then the process is said to be stationary. And we shall be concerned in the rest of the course with stationary random processes only. In other words, the probability density functions that we write shall be independent of the time origin. If the probability density functions are independent, obviously the averages that we take shall also be independent. Isn't that right? Any average that we take, expected value of any function of x1, x2, x3, because after all the average is going to be taken by multiplying by small p and integrating over all possible values of x1, x2 and x3. Alright? So you understand what is not stationary is non-stationary. Alright? Most of the processes, unless otherwise mentioned specifically, most of the examples and processes that we shall consider, we tacitly assume that the processes are stationary. Finally, another involved concept is ergodic and non-ergodic. It's a bit involved concept at this stage, but when you do your communication course, things will become more clear. But for our purpose, we define an ergodic process as a stationary random process. Ergodic process is a stationary random process, that is the probability density functions are independent of time origin, in which strict definition is almost all members of the ensemble have the same statistical characteristics as that of the ensemble. Is the point clear? This is a class of 205N, alright? Now, the character of one of the members of this class can be quite different from another. One may be very kind, the other may be very harsh. Alright. Suppose all of you, I take one character and say all of you are very kind. Alright. Then you will be called an ergodic assembly. It's a random process. All your other characteristics may be different, but in respect of one character. Now, if in respect of all statistical characters, every member of the family has the same characteristics as that of the ensemble, then it is called an ergodic process. Now, to be more precise, more concrete, the necessary and sufficient condition for a random process being ergodic is, one is stationarity. Stationarity is essential, and the other is that the ensemble averages are equal to the time averages. This is one of the necessary and sufficient conditions for a process to be ergodic. That is, ensemble average, let me illustrate this term, is equal to time average. Let's see what this means. What I mean is the following. Suppose I want to find out xn average, the ensemble average. Then you know this is equal to minus infinity to infinity x to the n p of x dx. On the other hand, if I want to find out the time average of x to the n, then what do? Time average of x to the n, I integrate from minus t to plus t, x to the n dt, xt to the n dt, alright, divide by 1, 2t, I've taken integral from minus t to plus t, and then allow t to go to infinity. This is the time average of one of the samples, isn't that right? I concentrate on one random time function. Now, an ergodic process is characterized by these two quantities being equal. That is, the ensemble average is the same as the time average. And this facilitates computation. We may not know the total ensemble. We may know only one member of the family, and we know the process is ergodic. Then all calculations can be carried out in the time domain.
Sir, but in this case, the ensemble average is not dependent on the specific random process that we take. I mean, there is a set of random processes.
There is not a set of random process is one. The process is one, it has members of the family.
Right. It is independent of the member of the family
Correct.
that we take. But won't the time average be dependent on the member of the family that we are?
That is what is characterized as an ergodic process.
That means for all members of the family.
That is what I started with, that each member of the family has the same statistical characteristics as the ensemble. Now, how can you characterize, let's say, an average in one member of the family unless you take the time average? That is the only variable left. Isn't that right? So, one of the conditions is that the time average is the same as ensemble average. It is only then that the process will be called ergodic. Now, I told you, well, a process which is not ergodic is non-ergodic.
So, but to prove this, we have to...
No, we don't prove it. We are not proving it. Proof we are not attempting in this class at all.
Even for definition, the
Even
second
for
should...
definition, sir.
Even for definition,
We have to take each one separately, each of the time functions.
Yeah.
So,
And the averages shall be identical. Because each member of the family has the same statistical characteristic as that of the ensemble.
no, sir, aren't we going in a circle?
No? This is the definition. No, wait a second. As I said, this is a necessary and a sufficient condition. This can also be used for definition. But the definition is that each member of the family has the same statistical characteristics as that of the ensemble, as those of the ensemble. And this is one of the consequences, but it can be shown. It can be shown, underlined. We are not showing it. Perhaps Professor Prasad, when he teaches digital communication, will show you. Or signal theory, that's one of the electives. They will show. But this is one of the necessary and sufficient conditions, that ensemble averages are equal to the time averages. This characterizes an ergodic process. And as I said, yes, Anurag.
Sir, but the ensemble average will depend on the instant of time at which we are taking those, we are taking the values of those.
That is
members of
correct.
the family.
But the probability distribution function is the same. Isn't it? Because it's stationary. By definition, an ergodic process is stationary. Now, that brings us to the next question. Are all stationary processes ergodic? No. A stationary process can be non-ergodic, and the most common example is this: a cosine of omega t plus theta, in which if theta is the random variable, then it can be a stationary process. But if a is also a random variable, then obviously the time average for each member of the family shall be different. Isn't that right? If capital A is also a random variable, then the maximum amplitude that it takes shall be different for different members of the family, and therefore this is a stationary process. I'm sorry, this is an ergodic process. No, this is a non-ergodic process. Non-ergodic but stationary. That is, probability distribution function, probability density functions can still be the same. It can be a stationary process, but it is non-ergodic if the amplitude function is also a random variable. This is a common example that is taken. Now, we come to the concept of a correlation function. You must have noticed that in Oppenheim, Wilsky and Young, that in many of the chapters there were problems on correlation functions, autocorrelation, which you have carefully avoided, because I wanted to introduce this ab initio without doing it in the context of an example, as Oppenheim, Wilsky and Young have done. A correlation function is a very important concept in any treatment of signals which have to be described statistically or by a probabilistic model. And the simple definition is that it is the expected value. Correlation function correlation function relates two random variables. Alright? Correlation function in respect of one random variable doesn't mean anything. It has to be defined with respect to two random variables, RV1 and let's say RV2. And the correlation function is defined as the expected value of the product of the two functions, two random variables. This is the correlation function definition. Alright? The definition is that it is the expected value of the product of two random variables. Now, the two random variables can come from the same process or can come from different processes. If they come from the same process, same random process, for example, it could be x of t1 and x of t2, alright, from the same random process. We are assuming, of course, that it is stationary random process. It could come from the same random process, that x of t1 and x of t2. Then the correlation function that we get is called the autocorrelation function. And as we shall interpret later, as we shall try to seek a physical meaning of the autocorrelation function, you will see later that autocorrelation function basically denotes how similar the shape of xt2 is to xt1. This is qualitatively the meaning of an autocorrelation function. From the same random process, how does the wave shape change from time to time? And this is the qualitative meaning. We shall make a quantitative description of this a little later. On the other hand, if the two random variables come from different random processes, let's say x of t and y of t, and we take two different time instants, the random variable over the ensemble of capital X and ensemble of capital Y, and we find out the expected value of this product, obviously we shall require a joint probability density function. We shall require this here also, but we'll come to this later. Now, if the two random variables come from two different processes, then the correlation function is given the adjective of cross correlation function. Alright, autocorrelation and cross correlation, and we shall consider both. The symbol for autocorrelation function is R, capital R, with X, and as you shall see later, the symbol for a cross correlation function is capital R subscript X comma Y. In that sense, autocorrelation is a special case of cross correlation, isn't it? R, and we should have written RXX for autocorrelation and RXY for cross correlation, but to keep notation simple, if it is autocorrelation, we write only one subscript, that is X. And Rx by definition is the expected value of X, let's say 1 and X2. They come from the same process but at two different instants of time. This X denotes that it is from the same process, and 1 and 2 denote that they are different instants of time. Now, obviously then Rx should be a function of the two times, right? Rx should be a function of t1 and t2, alright? And if the process is stationary, after all, Rx is an average, ensemble average, isn't that right? Rx, if you find that the expected value, you have to multiply by the joint probability density function and integrate over all possible values of x1 and x2. Now, Rx, t1, t2 if the process is stationary, then obviously it should be equal to Rx. You can increase T1 or decrease T1 by any amount. You can increase or decrease T2 by the same amount. That is, it should be independent of the time origin, therefore it should be T1 plus T, T2 plus T, if the process is stationary. The averages are independent of the time origin, and therefore if you increment T1 and T2 by the same amount, it should not matter. What does this mean? Same amount means you have shifted the time origin either to the left or to the right, depending on the sign of capital T. And time and averages, ensemble averages, are independent of the time origin, and therefore this should be the case. Now, if you put T1, capital T, let's say equal to minus T1, then obviously Rx of T1, T2 should be equal to Rx of 0 and T2 minus T1, which reveals the fact that the autocorrelation function for a stationary process should be a function of the time interval only. It should not depend on the time, on the origin of time, alright, on the origin chosen for time or the reference time. And therefore in notation, we keep the notation simple by omitting this and indicating this as a time interval by tau. And so we write Rx of tau, which immediately indicates that the process is stationary. Otherwise we should have written Rx T1, T2. Rx of tau therefore is defined as E of xt, where small t is arbitrary, times x of t plus tau. Alright. So it is the expected value of xt, x of t plus tau. T could be small t, could be t1, then this is t1 plus tau. Does it matter if we write t minus tau? Does it matter? No, it doesn't matter. And this immediately says that Rx of tau must be equal to Rx of minus tau. Isn't that right? If I call this as Rx of tau, then this is Rx of minus tau, which means that Rx of tau is an even function of tau. A very simple proof. Rx of tau, the autocorrelation function, is an even function of tau. Now, if the random process, in addition to being stationary, is also ergodic, if it is also ergodic, then Rx of tau could even be calculated in the time domain. In general, the time domain autocorrelation function, which you shall denote by this symbol, Rx of tau, time domain autocorrelation function, is defined as the average over time of x of t and x of t plus tau. Alright. The average, time average of this, which if I write it completely, it should be limit t tends to infinity 1 by 2t integral minus t to plus t, alright, x t plus tau dt. This is the time average of the product, alright. And if the process, this is called time autocorrelation function or simply SCF. On the other hand, this symbol Rx tau shall be taken as ensemble SCF. Alright. Time autocorrelation function and ensemble autocorrelation function. For an ergodic process, these two are identical. In other words, Rx tau is equal to Rx of tau. Alright, for an ergodic process. And the calculation, you can simply take the time average of xt and xt plus tau to calculate this. Otherwise, if you want to calculate the ensemble average, you require the joint probability density function. Alright, now what is Rx of 0? Rx of 0 is the expected value of xt and xt, and therefore is the expected value of x squared, which is simply equal to x squared bar. And if this is tau equal to 0, and if this is a 0 mean process, what does it mean? X bar equal to 0, then it is simply equal to sigma x squared for 0 mean process, or x bar equal to 0. All right. If tau is not equal to 0, if tau is not equal to 0, then the physical interpretation of Rx of tau is how much of the waveform of xt, how much the waveform of xt is retained in xt plus tau. Well, if it was a deterministic signal, if this was not a random time function, obviously all of it would have been retained. Isn't that right? If it was not a random time function, then xt and xt plus tau, the wave shapes would not have been different. It would only mean an advance by an amount of tau. All right. On the other hand, because it is a random time function, xt and xt plus tau may be quite dissimilar. So Rx of tau physically has the interpretation of how much wave shape of x of t, or how similar the waveform of x of t plus tau is to that of x, or in other words, how much of xt is retained, how much wave shape of xt is retained after an interval of tau. To put it on a on an analytical basis, let us consider a 0 mean stationary process, that is, we consider a process, a random time function xt with x bar equal to 0, and we consider the function yt, which is xt minus rho, some quantity rho, times x of t plus tau. Now, we want to minimize, we want to choose rho. The problem that we set ourselves to is choose rho such that sigma y squared, which is the same as y squared bar, because we have assumed a 0 mean random process, and this is a linear combination of two random processes, and therefore this shall also be 0 mean. All right. So sigma y squared is minimized. This is the problem that we set ourselves for, and we shall see that this brings in a physical interpretation of Rx of tau. Let us see what is the expected value of y squared. Expected value of y squared is obviously the expected value of xt squared. Now we must write the argument, plus rho squared x of t plus tau squared minus twice rho x of t plus tau. And you notice that expectation, the integration is a linear operation, and therefore we can write this as the sum of three terms. The first term would be x squared bar. Well, let us write this as y squared bar. First term would be x squared bar. Second term would be rho squared, again x squared bar. Why? Because the process is assumed to be stationary. Minus twice rho. What is the expected value of this? Obviously this is Rx of tau. Isn't that right? Expected value of the product xt and xt plus tau is the autocorrelation function, and therefore we can write, because it is a 0 mean process, sigma y squared equal to sigma x squared 1 plus rho squared minus twice rho Rx of tau. We wanted to choose rho, our problem was to choose rho such that sigma y squared is minimized, and therefore what we do is we differentiate sigma y squared with respect to rho and put the value to 0. Okay. If I do that, what I get is the following: sigma x squared times twice rho shall be equal to 2 Rx tau. Alright, this is the condition that minimizes, well actually it could maximize or minimize. You have to take the second derivative and then find out the sign. You can verify that, but this is the condition for minimum, and therefore rho for minimum sigma y squared is given by Rx tau divided by sigma x squared. This coefficient rho therefore is directly proportional to Rx of tau. It is not exactly equal to Rx of tau, it is Rx of tau divided by sigma x squared. So rho is given the name of a coefficient, that is correlation coefficient or coefficient of correlation. Well, I have written correlation coefficient for one purpose, that it is the correlation function normalized with respect to sigma s squared, and therefore it is sometimes also called normalized correlation coefficient. All right. Now let us see what is the range of possible values of rho. Obviously, I claim that rho lies between +1 and -1, +1 and -1. Well, let us see what happens when rho equal to +1. When rho equal to +1, if you find out the minimum sigma y squared, you will see that this is equal to 0. It is simple algebra. Take rho equal to 1 and then find out minimum sigma y squared, you will see that this is equal to 0, simple algebra, which has the physical interpretation that the two waveforms xt and xt plus tau are perfectly correlated. This is the physical interpretation, rho equal to +1. On the other hand, if rho equal to 0, that means nothing of x tau, xt is retained in x of t plus tau. So they are perfectly uncorrelated. Rho equal to 0, perfect uncorrelation, or uncorrelation is not a very good term, perfectly uncorrelated. All right. Why do you say perfectly uncorrelated? Uncorrelated is uncorrelated, so we can even exclude this. Rho equal to 0 means xt and xt plus tau have no similarity with each other. On the other hand, rho equal to -1, again by algebra you can show that rho equal to -1 gives you, I can tell you how much this is, twice sigma x squared. I think that is what is given. But the interpretation is that x of t and minus x of t plus tau, they are perfectly correlated. Rho equal to -1 means that x of t, you see rho equal to +1 means x of t and x of t plus tau are perfectly correlated. Rho equal to -1 means that the two waveforms are similar except for a change of phase by 180 degrees. All right. So this is the interpretation of rho, and through rho we get an interpretation of Rx of tau. Because rho is proportional to Rx of tau, and therefore autocorrelation coefficient physically means how much of xt, how similar x of t plus tau waveform is to that of x of t. And this I think is a good point to stop.